Hi, this archaeonomy video is about archaeological methodology, what we do and why we do it. This is a massive topic, but hopefully I can present it to you in a simple, generalized way so it's easy to understand without requiring an undergraduate degree in archaeology. Archaeological methodologies are determined by several factors: the type of site, the nature of the sediments, the theoretical approach the archaeologist is working from, budget. God, you can never escape budget. But it all boils down to asking questions of the archaeological site and extracting information from it. I'm framing this video based on the fundamental questions: what, where, when, who, how, and why. There'll inevitably be overlap and interaction between each of the questions and the information that we hope answers them, as they do not exist in a vacuum. For my example today, I'll be using the classic Windows Field wallpaper background as my virtual archaeological site to be investigated. I'll be keeping things generic, as these principles can apply to many sorts of sites all over the world. So first of all, what is there? Archaeologists will typically start an investigation into a property by checking historic records, maps, survey plans, looking for clues. Then, armed with that information, they'll do a pedestrian survey, walking over the site looking for features visible on the surface, using a gum digger's probe if the soil allows, to feel underground for features such as midden or buried stonework. Geophysical surveying is a non-intrusive way of gathering information about what's under the ground. There's various machines that can be used. Magnetometers such as fluxgate gradiometers are popular, as they're user-friendly, pretty reliable, and fast. They measure variations in the magnetic field between the ambient and the ground level using a pair of coils. To create a picture of the variations, features such as fire features, stonework, significant earthwork show up on these surveys, which are precisely what archaeologists normally want to locate. Metal shows up particularly well, and if a site contains too much metal, or the sediments are rich in iron oxides, the readings from the metal can swamp everything else. The maps produced by geophysical surveys often look a little like a low-res image of the surface of the moon. So conveniently, here is our geophysical survey map of the Windows Field. Spot the lunar lander if you can. The next step up in the degree of intrusion on the site is test pitting. Small pits excavated either by hand or by a machine, cutting through the various layers to see what's there. Where a geophysical survey has taken place, these test pits are usually targeted to where the survey showed anomalies in order to test what they are. It's an important aspect of geophysical surveying called ground truthing. So let's place some test pits and see what we have here. There's different kinds of archaeological information a test pit can reveal. First, layers of soil called stratigraphy will be visible in the sides of the pit. These layers may have formed naturally by human action or some combination of the two. The law of superposition applies here. Under normal circumstances, the lower a layer is down in the deposit, the older it is. Archaeological features are non-portable evidence of human activity, such as post holes, pits, trenches, stone or brick structures, hearths, middens, or compacted earth floors. They can be encountered in plan while digging, or be visible in the side of the pit in section, and it often can be seen at what point in the stratigraphic sequence that the feature was created. Artifacts are portable pieces of material culture, objects made by people at some point in the past. They can be as simple as a crudely flaked stone tool. If it had an artificer, it's an artifact. Environmental samples can be taken as well. Pollen, charcoal, volcanic ash, even microscopic silica remnants of plant structure called phytoliths can be sampled and analysed. But what if there was no geophysical survey? It's by no means a universal technique. Maybe the soil type is not suitable for a magnetometer survey and no other equipment is available. Or simply that geophysical equipment is too expensive for the project budget. In that case, assuming there's no historic plans or other information to help target a test pitting regime, test pits can be dug at regular intervals, a grid pattern for example, to get an impression of what is present in the site. Some archaeologists use a grid and a random number generator to randomize the location of their test pits. The next level of intervention is both more destructive and more informative. Therein lies the trade-off. Maybe you have a geophysical survey to guide you, maybe you don't. Test trenches, often excavated with a mechanical digger to save time and therefore money, can be cut across the site to see what the stratigraphy is like, discover features, and if you're lucky, it's always harder with a mechanical digger than working by hand, find artifacts. Obviously, the more soil you move, the greater chance of encountering features, and the greater chance of getting some insight into what's going on in a site. Moving on from what to where. When a feature or artifact is found, it's crucial to understand the context of the find. Where is it located, both spatially and stratigraphically? Historically, spatial location has been recorded by creating a control grid over the site to be excavated. It serves as an aid for hand-drawing the features on a plan and for recording where artifacts are found. Increasingly, the use of electronic total stations and high-accuracy GPS systems means that features and artifacts can be digitally mapped in 3 dimensions without the need for a grid. I know of archaeologists who use 3D laser scanners on archaeological features as well. Vertical control is maintained in 2 main ways: excavating down layer by layer, documenting what layer a feature is dug into and what layer or feature any artifact was found in. If a layer is too thick to practically excavate it in one go, it can be reduced down into fine thickness slices called spits. Also, we can retain vertical walls of earth called balks, which allow the profile of the stratigraphy to be seen clearly and documented. When they're no longer needed, they can be knocked out to reveal any features or artifacts that are contained within them. A key question for archaeologists is when. When was the site constructed? When were the layers deposited? When was this artifact made? They have a variety of ways of establishing this. The features or artifacts themselves may provide clues. For example, some coins handily have dates printed on them. But let's assume it's not going to be that simple. Context and stratigraphy are very important. For example, in New Zealand, we've had a number of large volcanic eruptions in the past, spreading layers of ash across the country. If those ash layers can be identified in the stratigraphy, and the feature or artifact was found in between them, the known dates of these eruptions start to narrow down the potential date of the deposit. In some parts of the world, when you find wood and charcoal, dendrochronology can quite accurately date an archaeological deposit. The growth rings of trees vary depending on climatic conditions, creating patterns of thick and thin rings like a barcode in the rings of trees. These patterns will be more obvious where the climatic conditions are harsh and variable. By overlapping wood samples using these patterns from different trees of the same species of different ages, a wider picture can be created. Depending on the species and location, this record can go back thousands of years. These dendrochronological sequences can be very accurate indeed. In fact, they're actually used to calibrate the next most famous method of dating, radiocarbon dating. To carbon date an object, it needs first of all to be carbon-based, such as charcoal, wood, bone, or shell. And the sample needs to be sizable enough to use, although a technology called accelerator mass spectrometry means that the sample sizes can now be much smaller than they used to be. Carbon dating compares the amount of a radioactive isotope of carbon called carbon-14 in the object compared to a baseline. Allowing for the rate of radioactive decay, an object, and therefore every other object in the same context, can then be dated. Carbon dating has its limits. It's not a magic bullet. The half-life of carbon-14 is around 5,730 years, meaning that with samples of extreme age, say 50,000 years, there's going to be practically no C14 left in the sample. And therefore, it can't be carbon dated. Similarly, the mass burning of coal and oil since the Industrial Revolution has artificially reduced the amount of C14 in the atmosphere, making it very hard to use carbon dating on any sample from the beginning of the Industrial Revolution in Europe on. Samples can also have inbuilt age. If your charcoal sample is heartwood from a very long-lived tree, the date you'll get will not be the date it was burnt, but the date that the tree last absorbed carbon from the atmosphere to that part of the trunk, which could be 100 years or more earlier. When taking C14 samples, we prefer tiny twigs or seeds if possible to minimize the inbuilt age issue. We often use seashell, which requires other factors to be taken into account, as the C14 intake will be different for a marine organism compared to a terrestrial one. Alright, enough when. Let's move on to who. On historic sites, this can be a lot easier question to address than on prehistoric sites, nailing down who your site is related to on various levels. Are we talking about Romans, Egyptians, Assyrians? Are we talking about nobles or peasants? We can learn more about who the creators of archaeological sites were in different ways. Historic research can tell us what was written about them. Studying the artifacts and features they made can give us insight into the creators themselves. In fact, many prehistoric peoples are named by scholars based on the style of the ceramics they used. For example, the Beaker people of Europe, or the Lapita culture of the Pacific. Archaeologists can also reference ethnographic studies from the past that can tell us directly how some people lived, and also provide comparisons to long-dead cultures. Getting now to some more modern techniques, facial reconstructions can be done on skeletons to try and see what they looked like when they were alive. Most recently, DNA analysis of their remains can show us their ancestry in great detail. Major studies have occurred primarily of mitochondrial DNA, which is passed from mother to child, but are now also looking at the Y chromosome to trace paternal ancestry. These studies have plotted human movements around the world going back thousands of years. Finally, we come to how and why was the site made. Anyone who's been interrogated by a small child will understand how the why question can get frustrating. Understanding the thought processes of ancient peoples can be very difficult indeed, especially since the evidence we're working with is inevitably fragmentary and limited. Generally, all we can do is provide our best educated guess, creating a theory, keeping Occam's razor in the back of our minds, and as new evidence is unearthed, update and revise the theory to reflect the current body of evidence. Archaeology is not a science, but we should adhere to scientific principles. One aspect of archaeology, experimental archaeology, allows us to test these theories and see how practical they really are. Lessons from this work can help refine and hone our theories on how and why people did what they did in the past. One example of experimental archaeology is HEMA, Historic European Martial Arts. Scholarly martial artists have taken weapons and equipment that are long obsolete on modern battlefields, referred to surviving combat manuals and other historic records, and resurrected as close as can be done lost martial arts. Some, such as rapier fencing, sabre and longsword, are more straightforward, as multiple manuals exist and can be consulted, while others, such as sword and shield, require far more experimentation and trial and error. People like Matt Easton of Scholar Gladiatoria and Roland Warchecker are at the forefront of the HEMA community. I personally have done a little HEMA and really enjoyed it. Given my interest in the New Zealand wars, I took up black powder shooting in order to gain understanding of the weaponry used by the British and colonial soldiers and the Maori warriors. I definitely think my understanding of how and why they did what they did has improved from learning how to use, maintain, and create the historic ammunition for their weapons. I hope this video has given some insight into archaeological methodology. It's been a strange video, but archaeology is a strange discipline. Thanks for watching, and please like, comment, and subscribe. Cheers!